When spectral lines were studied with high-precision instruments, very fine transitions were observed, new lines very close to each other. Bohr's atomic model could not explain this fine structure, which requires taking the analogy of the planetary motion of the electron to the next level, plus some relativity. Arnold Sommerfeld is considered the great teacher. He was the mentor of remarkable physicists, including Wolfgang Pauli, Werner Heisenberg, Hans Bethe, and Peter Debye, all Nobel laureates, in addition to Rudolf Peierls, Walter Heitler, Wilhelm Lenz, and a long list of distinguished scientists. Sommerfeld was in Germany, while J.J. Thomson was in England. Thomson was a great experimentalist, Sommerfeld a great theorist. Although most videos about him focus on his 84 nominations to the Nobel Prize, or his introduction of the fine structure constant, which is presented as an almost esoteric topic, in this video I want to show you his most significant contribution to early quantum physics. In July 1913, after publishing the first paper of his trilogy, Bohr got a letter from Sommerfeld, who was very impressed by his atomic model. Just like Rutherford, Sommerfeld was worried about how the mix of quantum ideas and old mechanics seemed to work, but without understanding what the electron was really doing. Sommerfeld was deeply interested in explaining observations in spectroscopy, so Bohr's model captured his attention. It really looked like a promising path to understanding some unexpected behavior of spectral lines. In 1897, the Dutch physicist Peter Zeeman discovered that a magnetic field could affect the spectral lines. He observed that the width of some lines increases proportional to the magnetic field. Better instruments show that some lines in fact split into several lines in the presence of a magnetic field. This phenomenon is known as the Zeeman effect. In a similar manner, in late 1913, Johannes Stark in Germany and Antonio Losurdo in Italy independently discovered a similar effect when using an external electric field instead. This splitting of spectral lines was mysterious, as if a single line could be pulled apart into several lines by the external fields. Everyone wondered, where do these new lines come from? Are they created by the external field? Are they all superimposed and the external field just separates them? Stark even considered that hydrogen could have several electrons. Another unexpected splitting of spectral lines was discovered by the Americans Albert Michelson and Edward Morley in 1887. In the same year that they did the famous Michelson-Morley experiment to measure the luminiferous ether, they reused the high-precision interferometer to scrutinize spectral lines of several elements and found sets of lines very close to each other that could not be explained by any of the many empirical formulas proposed since Balmer. This splitting of spectral lines became known as the fine structure. Oh yes, there are two Michelson-Morley experiments in the same year, even with the same instrument, and both had a significant impact in the development of modern physics, the first for special relativity and the second for atomic physics. For Sommerfeld, all these unexpected lines screamed some sort of fundamental physics happening at the atomic scale. This is why Bohr's atomic model was so attractive. Moreover, during the last peaceful days of 1914, Bohr's model received a strong boost after solving the problem of peculiar stellar spectra and explaining the Frank-Hertz experiment. In the summer of 1914, Sommerfeld wrote a letter to Paul Langevin, the doctoral advisor of the distinguished de Broglie brothers in Paris. Apparently there is much truth in Bohr's model, and yet I believe that it has to be reinterpreted in a fundamental manner. Sommerfeld imagined hydrogen with its single electron, but with more than one possible state hiding in each of Bohr's orbits, which would reveal their existence only under the presence of an external field. Sommerfeld was a great theorist, and with this insight, he recognized the deep connection between symmetry and degeneracy, which was well known in classical mechanics. In case you are not familiar with the term, degeneracy refers to the idea of two different states having the same energy. If you have ever studied linear algebra, you might remember that for some matrices, two eigenvectors can have the same eigenvalue. This phenomenon is also called degeneracy. Sommerfeld's idea is the same, but instead of eigenvectors with the same eigenvalues, he refers to electron states with the same energy. But what do matrices have anything to do with the energy of the orbiting electrons? That's coming soon. This observation of interpreting the description of a physical system as an eigenvalue problem became one of the fundamental postulates of modern quantum mechanics, something that Sommerfeld doesn't get enough credit for. Back to the degenerate energies, imagine that the energy of the electron is given by this relation, where n1 and n2 are two independent quantum numbers labeling the electron states. Note that the states 2, 0 and 1, 1 have the same energy. This would be a set of two degenerate states. They are different because they have different quantum numbers, but they have exactly the same energy, so they cannot be distinguished. Remember that spectral lines are produced by the gaps between energy levels. An electron transitioning from some initial state to any of these two degenerate states will appear as a single identical spectral line. Sommerfeld imagined that introducing an external field could break some symmetry of the system, which would remove the degeneracy, and the two states would have a slightly different energy, producing the observed extra spectral lines. And as I will show you in a minute, Sommerfeld was on the right track. At a time when almost nobody knew about young Niels Bohr, Sommerfeld invited him to give a seminar in his group in Munich in July 1914. In addition to his atomic model, Bohr presented a follow-up paper published early that year in which he describes an electron orbiting the nucleus in a perfectly circular orbit and then turning on a weak electric field. Because of the electrostatic force acting on the electron, the orbit will be deformed. The orbit might at every moment be considered as an ellipse with the nucleus in the focus. I mention this because most textbooks claim that Sommerfeld was the first person to think about elliptical orbits. However, Bohr himself had already suggested this possibility. Nonetheless, he did not solve the problem. As he wrote on the same paper, a detailed investigation of the motion of the electron might be very complicated. Still, under some assumptions, Bohr showed that the electron in this case could have different energy levels in agreement with the Stark-Lassurdo effect. Nevertheless, Bohr's idea had a problem. It only splits the energy levels into two, called a doublet, whereas experiments showed the existence of doublets but also triplets. It is tempting to imagine that this result was Sommerfeld's initial motivation to explore elliptical orbits. However, given his strong mathematical background, my personal interpretation is that these new results by Bohr were just the confirmation of his suspicion on the idea of new electron states hiding under the same energy level. This degeneracy could be a consequence of the symmetric circular orbits. Allowing more general elliptical orbits could break the symmetry, the degeneracy gets removed, and the different states are revealed. But this is just my guess based on what I have read in his papers. In any case, Sommerfeld wanted to understand the fine structure splitting, which doesn't need any external field. During this time, Sommerfeld corresponded regularly with theorists and experimentalists, bouncing ideas, mostly the Germans Friedrich Paschen, famous for his law describing the voltage necessary to start a discharge between electrodes, and the set of spectral lines named after him, and Karl Schwarzschild, who would later become famous for finding the first exact solution of Einstein's equations of general relativity describing black holes. But before this work, Schwarzschild made significant contributions to the theory of spectral lines. In 1914, World War I interrupted communications between scientists all over Europe, and many of them were drafted, many to serve as radio operators or to calculate projectile trajectories. Sommerfeld served as a scientific advisor in an artillery unit, but was not sent to the front. He stayed in Munich and continued his work. His assistant, Wilhelm Lenz, was sent to France as a radio operator, but they exchanged letters regularly. With the goal of explaining the fine structural lines, Sommerfeld realized that for extending Bohr's atom to include elliptical orbits, a new quantum number would be required. In fact, he introduced a general quantization rule for periodic systems with any number of independent coordinates, in which the integral of the momentum over the corresponding conjugate variable for a full cycle is an integer times Planck's constant. And this could be applied to every degree of freedom of the system, completely generalizing Bohr's approach. A very similar idea was independently proposed by William Wilson at King's College London in 1815. Today, this is known as the Wilson-Sommerfeld quantization rule. Using this rule, Sommerfeld identified the two relevant degrees of freedom for his system, the angular coordinate phi and the radial coordinate r. With this, the quantization rules become these relations, where n phi and n r are the two quantum numbers parametrizing the allowed states of the electron. The first integral is trivial. It is just Bohr's result. The second is highly non-trivial. I will just outline the setup and you will understand why Bohr stayed away from this. The total energy of the electron orbiting a nucleus of charge Z times E is this, where the speed has a radial component and an angular component, and it can be written in terms of the radial and angular momenta PR and L. These relations are easy to prove using Lagrangian mechanics, but if you check any celestial mechanics textbook, you will find an alternative and longer derivation only using Newton's second law. The total energy can be written in this form, from where we can solve for the radial momentum PR. Now, this is what we have to integrate over the full orbit. Just to simplify the notation, I will define these constants a, b, and c to rewrite this ugly expression like this. Solving this integral is a hard and very long exercise that requires extensive knowledge of complex analysis. This is why physics students spend a couple of semesters with courses on mathematical methods for physicists. These courses are like a year-long bootcamp on solving differential equations and evaluating ugly integrals like this. Using this dark mathematics, the integral is given by this. Veterans of complex analysis will recognize Cauchy's residue theorem. In case anybody wants to check the details, in the description you will find a link with a step-by-step solution. Plugging the definitions of A, B, and C back, we can impose Sommerfeld's quantization and then solve for the energy to find this. Let me bring back the electron's energy in Bohr's model for comparison. Here I have just renamed the combination of constants simply E0. The energy looks almost the same as in Bohr's model. After such hard work, the result seems quite disappointing, because by simply redefining m phi plus nr equals n, we recover Bohr's formula. It appears as if nothing new has been found, but there is more than meets the eye here. With the extra quantum number for elliptical orbits, Sommerfeld confirmed his guess of many other electron states hiding and appearing as identical spectral lines. In his paper he cheerfully wrote, "Allowing elliptical orbits has added no lines to the series. We again have the discrete Balmer series, but with numerous possibilities for generating them." Consider a particular spectral line of hydrogen, for example the blue line in the Balmer series, with a wavelength of 434 nanometers or a frequency of 691 terahertz, corresponding to a spectral line with an energy of 2.86 electron volts. In Bohr's atom, this line corresponds to the transition from the level 5 to the level 2. In Sommerfeld's model, there are 5 states in the initial level in which the sum of the quantum numbers is 5, and 2 states in the final level in which the sum of the quantum numbers is 2. With so many states, we find 10 possible transitions that will produce light of the same frequency. In other words, there are now 10 possible ways to generate the same spectral line. Remember that the frequency or wavelength of the emitted radiation that makes a given spectral line is determined by the gap between the energy levels. For this reason, all these 10 transitions generate exactly the same line. This is why Sommerfeld writes that his elliptical orbits added no lines to the series. His model produces the same result as Bohr's model, but proves that the generated states are possible. Sommerfeld's energies and the corresponding frequencies look almost identical to the energy of Bohr's atomic model, except that the principal quantum number now is the sum of the two independent quantum numbers. Another difference is that now electrons can move in exotic orbits. Using this extended version of the electron energy levels, he presented his generalization of Balmer's formula for the frequency of the spectral lines produced by the electron transitions at the meeting of the Bavarian Academy of Science in December 1915. Sommerfeld was clearly on the right track. All that was needed was an extra contribution to the energy levels that could split the lines to explain the fine structure. He was working on this while at the same time studying what he considered a beautiful distraction from quantum physics, and the most important physics publication of the year, Einstein's General Theory of Relativity. Just 1 month earlier, in November 1915, Einstein had finally completed his masterpiece, a new theory of gravitation 10 years in the making that extended his already remarkable theory of special relativity and Newton's law of gravitation. One of the examples of the success of the new theory was that it could finally explain the odd behavior of planet Mercury, whose elliptical orbit is not fixed. Einstein showed how his equations predict a small relativistic correction to the elliptical motion of the planet closest to the Sun that accounted for the mismatch between theory and observation. Could this idea be adapted to the elliptical orbits of the electrons? Of course, the force that keeps the electron in orbit is the Coulomb attraction instead of gravity, but this small relativistic correction to Mercury's orbit might have inspired Sommerfeld to consider the effects of special relativity on the electron's orbit. By the way, I am considering a future video series on relativity. Let me know in the comments if that would be of interest. It took Sommerfeld just 1 month to present a refined version of his elliptical orbits. He realized that an electron in the ground state of Bohr's model would move almost at 1% of the speed of light. This can be directly obtained from Bohr's model. As we proved in an earlier video, the speed of an electron in the ground state is given by this. Plug in the formula that we found for the radius and dividing by the speed of light, we get this quantity. Plug in the values for hydrogen, this is slightly below 1%. Notice that this quantity has no units. And just like Planck's constant shows up in any quantum calculation, this dimensionless quantity shows up in every quantum calculation involving the interaction of electrons with light. Today, it is known as the fine structure constant and is denoted by alpha. It is usually approximated by 1/137, and it is the topic of many not very scientific discussions. But I am digressing here. Just keep in mind that this is not how the famous constant was introduced. The fine structure constant will come back soon. Sommerfeld realized that for his newly introduced elliptical orbits, the electron could move much faster at the closest point to the nucleus, just like planets move faster at the periastron. Additionally, from the formula above, the speed of the electron also grows with the atomic number. Sommerfeld decided to treat the electron as a particle obeying the rules of special relativity. The phi quantization remains the same, so the result is the same as in Bohr's model. For the R quantization, things are different. The electron's energy now is given by this expression. The first term is Einstein's relativistic energy of a free electron, and the second term is the Coulomb interaction potential. And now we follow the same steps as before. We write the total momentum of the electron as the sum of radial and angular momentum components, solve for PR, and integrate over a full orbit. The result looks just like our previous calculation, but note that the constants A, B, and C are way more complicated this time. Plugging them back into the result of the integration, we get this. Now we impose the radial quantization by setting this equal to nr times Planck's constant. Notice that the overall factor 2 pi on the left-hand side can be taken to the right-hand side and h becomes h bar. These are the two equations found using the Wilson-Sommerfeld quantization rule. The next step is to find the energy. Combining these two relations and after some algebra, we find this expression. Now this looks like a completely different relation for the electron's energy levels compared to Bohr's model. If you read Sommerfeld's paper, you will find that he presents a Taylor series instead of this closed form. He thought that all the terms were so complicated that decided to define a dimensionless parameter that he called alpha and use it as a perturbative parameter. I know what you're thinking. This is how Sommerfeld introduced the fine structure constant. But not that fast. He used a slightly different definition for his alpha. Again, this is not the fine structure constant, yet. For simplicity, I am using the true fine structure constant here. Sommerfeld's version makes everything messier. Following Sommerfeld and expanding the energy as a Taylor series in alpha, the energy levels become this sum of terms, where the powers of alpha beyond 4 have been neglected. The first term is just the rest mass of the electron. Notice that the second term is exactly what we found in the non-relativistic case, and the third term is the relativistic correction. Do you recall how in the non-relativistic case the two states 2,0 and 1,1 had the same energy? Since there is no energy gap between these two states, Sommerfeld concluded that no new spectral lines could appear. Now, using his relativistic formula, these two states have different energies. The appearance of this tiny energy gap between the two states implies that they are physically distinguishable. Sommerfeld discovered that the elliptical orbits plus relativistic corrections can split spectral lines. This is the reason for the fine structure splitting discovered by Michelson-Morley. Sommerfeld presented his refined extension of Bohr's model in January 1916 at the meeting of the Bavarian Academy of Science. This became known as the Bohr-Sommerfeld model of the atom. The definition of alpha introduced by Sommerfeld comes from the ratio of two angular momenta in Kepler's orbits. After he completed his paper, he sent it to northern France, where Wilhelm Lenz, his assistant at the Western Front, reviewed it and praised it, but also suggested modifying the definition of alpha. Lenz suggested the form that we know today. This definition allows simple expressions instead of the long and messy formulas used by Sommerfeld. Therefore, it was Sommerfeld who introduced alpha, but it was Lenz who defined it. This is how the fine structure constant entered physics. Sommerfeld followed the advice of his assistant and acknowledged him in the final paper. Alpha, as suggested by Lenz, has the nice property of characterizing the speed of the electron in the ground state, but more importantly, it characterizes the strength of the electromagnetic interactions. I mentioned earlier that the value 1/137 has reached almost a mystical level. I personally don't understand this fascination with numerology. In fact, as a joke, I created this fine structure constant bingo card with mostly scientifically meaningless facts about alpha. Long ago, I realized that alpha is also equal to the abundance of uranium-235 in natural uranium. Watch any video about the fine structure constant and you will hear little about Sommerfeld's work, but a lot about how alpha is a fundamental, mysterious, and even magic number. You will see quotes from famous people and even discussions about aliens. Sommerfeld reached Paschen to experimentally confirm his model. Now he could predict the exact frequency of the new spectral lines. Paschen attempted careful measurements of the H-alpha and H-beta lines in hydrogen and was able to photograph them as double lines, but the images were blurry. Paschen wrote back to Sommerfeld that he was not ready to accept this as compelling evidence. The effect could be due to some experimental artifact. The splitting was just too small. Note that the gap is proportional to alpha to the fourth power, making this splitting really hard to observe. Then Sommerfeld realized that his formula contained what he called a magnification factor. The term z to the fourth power could dramatically amplify the splitting. By studying helium instead of hydrogen, the lines would separate 16 times more. He asked Paschen to try again using helium lines. The two men exchanged letters on a weekly basis. In May 1916, Sommerfeld got a special congratulation letter in the mail. My measurements are now finished and are in wonderful agreement with your fine structures. Without your theory, these results would not have been found. Sommerfeld's predictions were experimentally verified. Sommerfeld and Paschen arranged a coordinated publication of the theory and experimental results. In July 1916, exactly 3 years after Bohr's model was published, Sommerfeld and Paschen published their results. Sommerfeld explained his extension of Bohr's model, including how and by how much the spectral lines would split. Paschen described his experimental setup and the photographs of the spectral lines and their fine structure, confirming Sommerfeld's predictions. Paschen measurements allow determining the fine structure constant from atomic spectra, and Sommerfeld had a remarkable idea. This new measurement serves as a cross-validation check of several fundamental constants. Comparing alpha to independent measurements of the electron's charge, Planck's constant, and the speed of light, they all perfectly agree. For the fans of numerology, I have one more for you. Sommerfeld published all his results in July 1916 as a very long article. It has exactly 137 pages. In the following weeks, Sommerfeld received one congratulating letter after another. In particular, Albert Einstein, whose general relativity had inspired Sommerfeld to add relativistic corrections to the electron's orbits, wrote in August, "Your spectral analysis number among my finest experiences in physics. Only through them Bohr's idea becomes entirely convincing." In 1918, when Max Planck received the Nobel Prize, in his Nobel lecture he compared Sommerfeld's work with the mathematical prediction of Neptune's orbit in astronomy. And in the words of Arthur Haas, who was proposing quantized orbits at the first Solvay conference in 1911, Paschen's measurement implies a brilliant success not only to the ideas of Bohr and Sommerfeld, but also of the theory of relativity. Sommerfeld's atomic model is usually left out in most textbooks, maybe because of its mathematical complexity compared to Bohr's model, or because it was quickly replaced by quantum mechanics. Just like Bohr's, Sommerfeld's model does not explain the behavior of systems having more than one electron. It does not explain the Zeeman and star effects, and the quantization rule only works for periodic motion. Moreover, it was later found that a complete understanding of the fine structure of the spectral lines requires the introduction of the electron's spin. Nevertheless, when Paul Dirac developed the complete relativistic quantum theory of the electron, he found that when expanding the energy as a Taylor series of the fine structure constant, the result is identical to what Sommerfeld found. Interestingly, it was Sommerfeld's most famous student who redefined the way the new quantum theory should be developed. Werner Heisenberg realized that we never measure the electron in the atom. We don't see how it moves. We never observe orbits at all. We only observe spectral lines. Heisenberg introduced one of the most radical ideas in modern physics. Stop trying to describe how the electron moves. The new quantum theory should abandon classical trajectories and focus only on the observed outcome of experiments.